Welcome back, everyone. In this video, we'll be finishing up the area between two curves section. Now in this one, the main purpose of this one is to show you that if you have things in terms of functions of y, you can still approach it the same way as far as graphing it and looking at the area. You just have to be a little more careful on what top and bottom means. So this one says find the area of the region enclosed by two curves. You have x equals 45 minus 5y squared and x equals 5y squared minus 45. Now automatically when I see x equals, as far as my equations go, I'm thinking this is going to be horizontal. The rectangles are horizontal. And the reason for that is because our function is really going to be a function of y. It's not a function of x like normal. And to help me explain that, I'm going to graph as well these two things, and Desmos can work just fine. Let's go ahead and do this. You can very literally graph them exactly like this. We have x equals 45 minus 5y raised to the 2 power. And we have x equals 5y raised to the 2 power minus 45. Now the hope is that in some type of pre-calculus class, you actually graph these things. These are parabolas because they're just a y squared. They're just parabolas that open left and right. But what the 45 here is doing, that's sort of telling you it's going to go each way 45. You can scroll out until you see it, but then it kind of messes with our scaling. So I'm going to adjust it here. The x values that we have are pretty much fine, but the y values are way too big. It's too skinny this way. So I'm going to make the y values just go between -10 and 10. And that's a lot better. But the idea here is when you have them like this, you want to visualize the rectangles going like this because you want it to be between the two curves. Problem is if your rectangles are vertical, like they normally are, then the top and bottom curve are actually the same, but you have to solve this and get it solved for y. And when you solve this for y, you get a square root with a plus or minus, and then you have to do a whole bunch of stuff. And a lot of times it's just harder. So rectangles are horizontal basically because we have x equals, but also if you graph it, if you draw like a horizontal rectangle like this, just follow my mouse cursor, the height of the rectangle is really given by the two curves this way, not this way. All right, so rectangles are horizontal since we have x equals stuff with y. That's probably the best way to think about it. Now, one thing I was mentioning in the first video is that when you have things like this, you have to be careful. What is going to help us be positive? Well, it's going to be positive if what we have here, if the height is positive as well. So do we want to do the green one minus the purple one or the purple one minus the green one? Well, what you should say, it's the green one minus the purple one, because when we are looking over here, you can tilt your head sideways. This is the positive x-axis. These are the bigger x values. So we want to use bigger x values for that reason. And when you set up horizontal rectangles, the area between two curves. So I'm going to go ahead and just write this down. For horizontal rectangles, well, everything is going to be in terms of y. So you're going to have y everywhere in your integral. It's from y equals a to y equals b. We still use the same letters, but it's just y values. And then it's right minus left. And then it's also dy because everything's in terms of y. Once again, it's right minus left. If you do left minus right, so if I just did one minus the other without caring in this problem, then what would happen is I would not get a positive area. I would get a negative area, and that would tell me I did it wrong. All right, so you can see the right one here. We're only looking in this section that it makes an area for. Notice that it didn't give us the bounds, so we have to figure out the bounds ourselves. But in this section here, the right one is the green one, and the left one is the purple one. So the green one is this one. This is the right function, and this is the left function. Now, thankfully, it doesn't switch at all, but it can't switch in this case anyway, because we're not told the x value. So we have to just locate the region. So this is the right, and this is the left. So as we set this up, I'm not going to point out A and B yet because we don't know them, but at least we know the right one is 45 minus 5y squared minus the left 5y squared minus 45 dy. Right, now what about the y bounds? So the bounds are on y, which means you want to think, okay, what y values am I ranging between? Well, my rectangles start down here and they go all the way up here. The y value starts at -3 and goes up to 3. Now you can either just use these numbers or actually solve it. So if you're without a calculator, how would you figure out these bounds? I'm going to go ahead and just mention we already know this is -3 to 3 from the graph. Or solve. And if you want to figure out the bounds, what we want to do is we want to go ahead and set the two equations equal to each other. So 45 minus 5y squared equals 5y squared minus 45. Because what we're trying to do is figure out where the graphs intersect each other. And anytime you want to figure out where two graphs intersect each other, you just set them equal and solve. So once we got this set up, you can start solving. The only power on y is y squared, which means we can get the y squared by itself. Add the 5y squared to each side. And then just to make our lives easier, we also want to take this minus 45 away from that, so we can add the 45 to each side. This cancels out and this cancels out. 45 plus 45 is 90 equals 5y squared plus 5y squared is 10y squared. Divide by the 10. And 90 over 10 is 9, so 9 equals y squared. And to finish getting y, we go ahead and do the square root of each side. When we square root, we know we get plus or minus, and the square root of 9 is 3. So plus or minus 3 equals y. And those are the bounds. Now, just like with x, and anytime you deal with y, when you set it up, you want the smaller number first. So if we want to find the area between this, if we did -3 to 3, that's correct. If we did 3 to -3, that'll give us the negative area. So the smaller bound is the -3 here. The larger bound is the 3. So a lot of times the problems that don't have the bounds and you have to figure them out, yes, there's some extra work to figure out the bounds, but usually you don't have to worry about them crisscrossing. You just see the picture, figure out the bounds, and then figure out which one is on the top, which one's on the bottom, or if your rectangles are horizontal, left or right. All right, so with that, we have everything set up. Once we have the area set up, and this is the only integral we have to do for this problem, we just integrate. So we got -3 to 3. Distribute the minus here. We don't need the parentheses in the first one because there's nothing to distribute. So we got 45 minus 5y squared. Distribute the minus sign. We got minus 5y squared plus 45. -3 to 3. 45 plus 45 is 90. 5y squared, but both negative, so -10y squared dy. And then we can integrate this. And we don't need any substitution because we can integrate each part. The integral of 90 is just 90y minus the integral of 10y squared. The 10 stays put. And the integral of y squared is y cubed over 3. And it's evaluated from -3 to 3. All right, so let's go ahead and plug it in. We plug in y equals 3. We get 90 times 3 minus 10 times 3 cubed over 3 minus, and then we plug in -3. 90 times -3 minus 10 times -3 cubed over 3. And just simplify, preferably by hand, but if you want to use a calculator, it's not the end of the world. 90 times 3 is 270 minus Well, luckily for us here, we can simplify a little bit without making the numbers too big, because 3 cubed over 3, we can cancel one of the 3's out with the other. So this is just 3 squared. And 10 times 3 squared is 90. Minus, and then 90 times negative 3 is negative 270. Minus, negative 3 cubed is negative 27. Now be careful about canceling out here because this is negative 3 cubed over 3. It's not 3 cubed over 3. So you actually can't cancel a power here because you are canceling out a negative 3 over a positive 3. So we'll go ahead and just leave this. 10 times negative 3 cubed is negative 270. The negative with the minus makes a plus 270 over 3. And then we'll just continue simplifying. 270 minus 90 is 180 minus, and this is also 90, so negative 270 plus 90 is negative 180. And double minus gives us plus 180 plus 180 is 360. And that's exactly what we get. And Wolfram Alpha, I'm sure you can do this as well. I'm not going to type it in. You can check it yourself if you'd like. But one thing I want to point out here is you'll notice that each one kind of gave us the opposite. So we got 180 in the first one and negative 180 in the second one. And the reason for that is this graph is symmetric. What I mean is that if we want to find the area of this entire thing, instead of making the rectangles all the way from negative 3 to 3, you can actually just start at 0 because the area of the top half and the area of the bottom half are exactly the same. So if you integrated from y equals 0 to y equals 3 and then doubled that answer, so this would be the 180 part, and then you double the 180, you get the 360. So you're welcome to use symmetry like that. Sometimes it can help you out. With this one, it saves a very little amount of time because what you're doing here is you're just plugging in 0 here. It does make it a little easier, but at the end of the day, plugging in the negative 3 was not really that bad anyway. But just something to look out for. If you graph and you see symmetry, you can try to take advantage of that. Right. But ultimately, that's really what this section is about. You can, if you set up your integral correctly, a big thing is recognizing, are we having left or right, up or down? Do we have to figure out the bounds? Are we given the bounds? Do we have multiple integrals to set up? Those are the main questions you want to go through your head. But once you get it set up, it's just an integration problem. And then they're no harder than the integration problems we were doing before. You just have to be able to set it up. All right, but I will see you in the next video.